Okay, so we're going to do antimicrobial surfaces. So the first thing we do is let's choose the component for our dispersion, and we start with polymer particles. We call them latex particles, and then which are basically acrylics mainly, and then zinc oxide nanoparticles, which has antibacterial effect. So what we are doing, we are blending this, and these ones are much larger than the zinc oxide nanoparticles. So we expect the zinc oxide nanoparticles to join up on the top surface. And in this case, we can see there's a bit of a bimodal distribution, so that's important for considerations of what the structure you're going to get at the end, but still they are much smaller than these ones. So if we blend them, we basically blend them at different ratios. This is the volume fraction of zinc oxide in the dried films. And then we are drying at different evaporation rates, because that's quite important for the structure you're forming. So sometimes medium evaporation rate is basically room temperature in the lab. Fast evaporation rate is under an infrared lamp. And a slow evaporation rate is an environment with really high humidity, so it takes really long to dry. Because all these processes are very related to how fast that the water interface goes down, if it is trapping more or less particles as it goes down. So this evaporation rate, as you can see, has quite an effect. So if you say a film on the top surface, and you can see that the round things are the latex particles, and if you have enough zinc oxide, you can start to see all these kind of formations that are on top of the latex particles. So we call these superstructures that are just basically made only of zinc oxide. We know this because we've done mechanical analysis with the IFM as well. So all these kind of structure with holes, there's no latex here at all. The latex is underneath. In fact, the latex is in these holes here, but there's a structure above, which is mainly made of zinc oxide nanoparticles. So we cannot get this structure where everything goes to the zinc oxide goes to the top, and you can see that these structures, they are taller, the slower we evaporate. So they are up to around 70 nanometers or something like that. So, and in fact, one of the things that we saw is, the surface coverage basically increases when you increase zinc oxide concentration, obviously, but for slow evaporation rate, the surface coverage is much higher at the same concentration compared with faster evaporation rates. So what we did is we tested, said, okay, this looks good, but do they kill bacteria? Do they not kill bacteria? So basically we have an agar where we have grown some E. coli, and then we put our coating here. So this is just an empty cover slip, and then these are with the coating. So you can see basically that, especially for the slow evaporation rate, there is a ring here where E. coli doesn't grow. So E. coli has this kind of yellowish color. So here is preventing the growth of E. coli. So this one is the most effective of all of them. So you can see the radius in which the bacteria is not growing. Basically, its low evaporation rate is the largest of all of them. And this thing led us to think, because these kind of superstructures that form at the top, they hadn't been reported much before. And it was just a few papers where they were also blending latex with inorganic nanoparticles, but normally they would never go above the latex particles, but we see that they form a structure properly on top of the latex particles. And they will kind of explain them in a way where they are just kind of going through the small nanoparticles, are going through the layer of latex particles at the top. And also there was another paper where they saw these kind of really superstructures at the top, but they had a different idea of why they were forming, because they only saw them at very high evaporation rates. So they're thinking that they have this small, large particles at the top, and the small particles are kind of going through the holes and going up and forming that structure. But that cannot really happen at really slow evaporation rates, even if the flow is not strong enough. So we said, well, so what's going on here? So we tried to explain why do we see those structures at really slow evaporation rates. So there is a model in the literature which basically can predict whether this segregation of the small and large particles during drying will happen. And you can basically make a phase diagram where you are putting, this is the Beckler number, which is related to the particle size and the evaporation rate. And here, this is the concentration of small particles. So these lines basically say, depend on the aspect rate, the size ratio. So the ratio of the size of the large versus the small. So 1 to 5 or 1 to 7 or whatever stage ratio you have. So basically for most of our particles, because they are laying on this side of the graph, that means that we are expecting the size segregation according to this model. So what how we explain our superstructures is basically saying, okay, we are within the region where we expect this size segregation. So the first thing that happens is we have a size segregation of large and small particles, especially at slow evaporation rate, you give them more time to segregate, so we have more small particles that are able to go to the top. In the case of fast evaporation rate, you have more trapping at the air-water interface, so you have some particles trapped there if you don't give them that much time. So in the end, when everything packs together, at slow evaporation rate, you have more small particles available to form these superstructures, and therefore they are taller. But for fast evaporation rate, they are not as tall because we don't have as many of them. So it was good to have some experimental insights on this. So then we said, okay, after proving that we can use it for antibacterial coatings, can we do something else? And we're thinking about abrasion resistance. So why abrasion? Well, durability is quite important for industry, also for the environment as well. If you put in a coating some nanoparticles, if they fall off easily, that's not going to be very good for you if they are toxic or if they are not environmentally friendly, or just for the sake of making them stable and durable. So one thing that we thought is, okay, if we have a binary blend, which is what we had before, just large and small particles, and we are talking about here latex and silica nanoparticles, then we form these structures at the top, like the zinc did with silica, and we have these kind of structures as well, but we expect a low surface stability because they are not bonding to each other. They're just inorganic nanoparticles, probably you can brush them off or rinse them off. But if we use a ternary blend, where we're using a second type of small particles, polymer particles, then we could expect to have a bit more bonding of these polymer particles with the silica nanoparticles, and maybe the durability would be better. So if we just mix these two latex particles and we make a film out of that, we get the same kind of superstructures with the polymer particles, small polymer particles at the top. If we add the silica now, the silica goes on top of the small particles. We have kind of like a three-layer thing where we expect the silica nanoparticles to be more stable than these ones because they have that polymer layer. But is that true? So that's what James did, one of my students, and basically what we did some abrasion testing. So we have the binary blend, the ternary blend, and they also did some annealing on the ternary. And he's basically doing an abrasion test where you have a felt pad and it's basically going over the surface for 100 times, and then he checks again the structure. So you can see for the binary blend, you just see the latex particles underneath. The silica is completely gone. So it's not stable at all. But if you add the second latex population, after abrasion, you still retain the particles. I mean, maybe the height is slightly lower, but you mainly retain all the structures. And with the ternary anneal, there's a bit of a mixed blend, I think. So we're not very sure about this. They still retain them, but it goes down quite high. But basically, the fact of adding a third population is really improving the abrasion resistance. He also checked using energy dispersion spectroscopy to see what is the amount of silica that is at the surface before and after abrasion. And you can see that for the binary blend, we go from about 20% of the surface to half of it. So basically, it's reducing half of the abrasion. Whereas with the ternary, everything is within error. So there's no change at all. The same with ternary. So it's definitely improving the durability of these coatings. Another thing that James was looking at that is the effect of particle interactions in the final structure of the film. So normally these polymer particles that I was talking about, they are negatively charged in water, usually acrylics. But so what happens if we add some cationic surfactants? So we have, for example, CTIB, and we have a positively charged surfactant that goes onto the surface and probably reduces the surface charge of that particle. And in fact, we can see that by measuring the zeta potential, that when we increase the concentration of surfactant, the zeta potential at the beginning is really negative, minus 60 millivolts, and going down to almost minus 10. So we are really reducing that surface charge. Again, we do blends of these less negative particles with silica, and we change the surfactants. So basically, this is the initial one without surfactant, there's similar structures, but then as we increase the amount of surfactant, you can see that that structure starts being less tall, and at some point it kind of disappears. And it looks like we are back to latex particles on top. But if you look closer, these are more particles. So we have latex that's completely surrounded by a layer of silicon particles. So basically, we have reduced the charge enough, so the silica can be on the surface of the latex. We can also see evidence from the size that we measure, the average particle size, which is around 100 nanometers larger, so it's not like there are diamonds of latex forming, but you have silica. So we have some evidence of far more particles forming. So what does that mean? We can see the effect of the surface, but what does that mean on the internal film structure? So we make cross sections of these films, and we can see if we have the latex particles are fluorescently labeled now, and we look at the cross section of these latexes, use the pure latex plus silica, latex plus silica plus the surfactant. Basically, in latex, you can see that the intensity is homogeneous all the way, more or less. Latex plus silica, you can see there is a reduction of intensity at the top because there is more silica, and it's not letting the light go through as well. And then when we go to latex plus silica plus CTAB, again, you have the more just homogeneous, so you don't have a layer here anymore. It's probably more clear in these integrated profiles. So you can see that the latex plus silica, there is a drop close to the interface in intensity, but for the other two, you don't have any. And we also did EBS of the cross section. And without CTAB, you can see the silicon with all the silicon element, which is the orange here in this, and you can see that it's quite concentrated at the top. You have quite an intense layer at the top, but when you add the CTAB, it's more distributed all over. So you can swap just by adding surfactant to different morphologies that you want to have within the film. Then, well, we also did a collaboration with some colleagues as well, some simulations to kind of make sure that these are more morphologies, what's happening. So they're again doing some Langevin equation or Brownian dynamic simulations, and basically they are putting together large and small particles, and they model two cases. One case where they don't like each other at all. And in that case, at the end, after trying this, you end up with a top layer of small particles. This is a view from the top. This is a view from the side. So you can see I have a big layer of small silica particles at the top. But if they make them so they like each other, then we have something that we expect, a more homogeneous distribution all the way through. This is good, and we are now just submitted this paper this, but we are very happy with these results and how can you control the architecture. So there is other stratification research that you can check. I'm not going to go into that just for the interest of time. I don't know how much time I have. 35. Okay. So yeah, there's something else I want to talk to you, which is this is the most recent thing that we've been doing, and this is looking into how can we develop fluorescence-based approaches to help formulation. So we have why do we do this? Well, normally in the formulation industry of all these products, inks, paints, coatings, etc., basically reformulating something means just adding more stuff. So if they have to change one component, they change it, and then they don't get the properties that they want in the product, so they add more stuff until they get the properties that they have. But obviously, you cannot keep on adding stuff. Definitely, that's not really sustainable. And also, we have also a drive now for using more renewable materials or from sustainable sources, and you really need to screen those and see if they work in a formulation. And so you need some methods that are more fundamental and more thorough, and that they can have like a high throughput as well. And that's what we are trying to do with what I'm going to explain later. So for this, we look at fluorescence lifetime, which for those of you that are not familiar, especially when some molecules get excited, they emit some intensity or some light, which is called fluorescence, and how fast this light is decaying, and how long does it last is basically called the fluorescence lifetime. But this fluorescence lifetime is important because it's very depends a lot on the local microenvironment. So it might change depending on the pH that you have there. It might change on the interactions with different molecules. It might change depending on the temperature. So it's really a really good representation of what's going on at a very local level. And it's good also because it's independent of the factors that may affect intensity. So if you take it very deep inside the sample, it doesn't matter. Your intensity will change, but your lifetime is going to be the same because you are very deep in the sample. So we're looking at these molecules that are called molecular rotors, and in particular this one, which is sulfonyl CY3. So basically, these molecules, they have two configurations, the trans and the cis. So when they are excited with the laser, they have this configuration, and then they decay or they transition into this other configuration, the cis, which doesn't emit. So in this process of going from here to here is when we measure the lifetime decay. And the interesting thing is that the lifetime is a really good signature of the viscosity of the environment. So when they have a very long lifetime, that means they have high viscosity, and when you measure a short lifetime, means that you have a very low viscosity. And they have been used for calibrating viscosity within environments, mainly biological applications, for cells and lipid membranes. So what we are trying to do is use this more in a, let's say, more industrial formulations. So we are using these rheology modifiers, which are these HEUR rheology modifiers, which are a type of modifier that can give the rheological properties that we need. And it basically has like a hydrophilic change in the middle, mainly PEG, kind of a PEG chain, and then you have a hydrophobic change on the sides. So basically, this what they are giving, they can form micelles, and they can also form at the appropriate concentration. They form this type of networks, and this is giving your dispersions a shear thinning behavior. So basically, when we increase the shear in the dispersion, the viscosity goes down. This is good for paint, for example, because when you are applying your paint, you want it to be easily to flow well. So that's the kind of behavior. When you're applying the shear, then it will flow well. So this is why they are in these modifiers. So, so we're very interested in where do these modifiers go, how do they interact with the different particles, the dispersion, and obviously this is going to be very dependent on the surface chemistry. Usually they thought that they would be like really creating this network in between particles, but nowadays it's believed that most of them they kind of stick to the surface and they stay around there. They also make some links in between. They associate particles. They are called associative rheology modifiers for that reason. So we are, for example, looking at this is just the viscosity versus shear rate for a solution of these rheology modifiers at different concentrations. And you can see that is they have a Newtonian behavior. Basically, it's shear rate versus viscosity is a constant. But what we are looking as well is looking at the lifetime when we put these molecules inside these dispersions with these rheology modifiers. And you can see that when you increase the concentration, this lifetime goes in this direction, which basically means that it takes longer to decay. So it's a longer lifetime because you get in a more viscous environment, etc. But what we are trying to is not only look at the viscosity of the dispersion, but look at the local environment. So you can decompose these lifetimes into three different. There's no one single lifetime, but that's mainly normally three different ones. So you can decompose this into three, each of these into three. And then we can know that this one, for example, we have now that is inside those micelles of rheology modifiers that form. You have this is the free molecular rotor. And we are trying to see what's going on with this middle one, which is the one that is changing viscosity. Trying to paint the microscopic picture of what's going on in that dispersion and what the interactions are. So if we blend this with the latex particles that we were talking about, we were talking before, so we have different types, surface chemistry, which was interesting. So this one basically is stabilized with polystyrene sulfonate, so just basically negative charges across the surface. There's another one which is macrograph, which basically instead of just the negative charge just on the surface, it has a polymer brush, which is charged. And then we have this rheology modifier that I want to talk about. So if we blend those two, the rheology modifier on the polymer particles, what we can see is that for a specific type of particle, so the one that has the polymer brush is called MRM. Instead of having a Newtonian behavior, we have shear thinning behavior. We have a change in behavior by measuring the rheology using a shear rheometer here. So it's interesting because that means that the surface chemistry is quite selective, and we have a system which has a different rheology. And this is expected just because like I said, the associations that happen in between particles. So what we are trying now, this is the last thing I want to say, is we are trying to, instead of using a shear rheometer, just measure the shear thinning behavior by using the fluorescence likeness. So not only taking a measurement of just the viscosity, but the dynamic behavior to be able to predict it using, in this case, a microfluidic channel. So we basically have this dispersion and we pump them through a microfluidic channel, and then we measure the lifetime of the molecular rotors inside. And we can see the difference. So each of these is for a different shear rate, or shear rate, sorry, pumping rate, pump rate. So the faster we go, we change this lifetime. If we translate this, and we represent here the lifetimes as a function of the shear rate or the pumping rate, you can see that shear thinning behavior. So you can see that the same trend, we can see it. So we, instead of having to go to the rheometer and put it there, etc. For example, if you're in a manufacturing plant, you just have to flow it through a channel, detect it, and then see whether you still have the CFC behavior that you wanted. And also, we are now in the process of, instead of having lifetime here, you can calibrate the lifetimes against viscosity. So we are calibrating the values so we can have a proper viscosity versus shear rate here, which we'll be able to do that. So we are seeing a lot of potential on here for non-invasive measurements with really high throughput. If you have to reformulate lots of products, you can quickly go through lots of them in this channel and pass them through and have a really quick measurement. So we are hoping this will be really useful. So conclusions, should I just go to them? So conclusion, just very briefly. So we have the size segregation in tri-colloidal blends, so it can be controlled for, can be used for controlling the final architecture. And we have harnessed this for two different applications at least, so for antibacterial coatings and abrasion resistant coatings. We also had a look at how important the particles interactions are. So there's a lot of understanding that still needs to be done, obviously. And then we think that the fluorescent lifetime is a really good parameter or really good signature of rheology in latex polymer dispersions, not only just one point of viscosity, but the whole dynamic rheological behavior. Looking forward, we are interested and we have projects in ionic solids. So basically, if we have positively charged, negatively charged particles, and see what happens there, because that's quite complex. So that leads to a lot of aggregation, and it's not easy to make a film out of that. But we are working on it. Taking forward that fluorescence lifetime screening and formulation, and also we are looking also some machine learning models to have a look at modeling these dry systems as well, and then try to optimize that and make it faster. And yeah, so that's all. So I'll just acknowledgements. These are the people that made all the work. I'm just presenting here. Sit in my office. So basically, so the guys that did everything, especially James, did all the work with the latex and silica nanoparticles. Well, Ichen she finished her PhD already, but the one who did the work with antibacterial coatings, and Tim is doing the work on fluorescence lifetime. Who's taking the lead on all that. And thank you to all my collaborators here, and to you for your attention. Thank you.
Thank you very much. Very interesting talk. I apologize for the inconvenience of the broadcast, but this is an experimental emission. So all experimentalists know experiments at the beginning have fluctuations. Fortunately enough, none of them have been catastrophic, and at the end we could stabilize in a rather satisfactory way the talk, and it has been very interesting. And now, if the audience, if there are questions, I have myself one, but Aurora first, please.
Well, very nice talk. So congratulations. So I would like to ask you about the drying process. The first part of your talk. How do you control the drying? It's basically you put a drop of your formulation or solution dispersion, I would say, and you watch it dry, or do you have what are the parameters that you control in the what you call slow? Maybe I missed it because it was in the beginning.
Yeah. So we mainly do casting. So we have then like I said, how fast that water interface is super important, because this process of size segregation only happens if it is fast enough to trap the small part, or which in case when it is solid also happens. So what we are doing is we have we are in a lab which is more or less temperature controlled, etc. So that one we have the medium evaporation rate is our standard for just leave it there, not do anything with it. We have for accelerating evaporation rate, we have two different ways. You can try it on a plate. Increase that, but normally that's a bit more complex and unstable. But we have also the infrared lamp. So we have a lamp, in fact, we bought it from a company that that incubates eggs. Mm-hmm. So they sell it for chicken eggs and stuff like that. It's like a lamp for keeping it warm. There's an infrared lamp that often you heat it. And then we have a little box where we are evaporating the ice water. And then that's the humidity goes up to 95%, something like that. And then it takes really long. So basically you can go from fast evaporation rate means that your film takes 10 minutes to dry. Medium evaporation rate will be 2-3 hours. The high evaporation rate, really slow evaporation rate will be 3-4 days.
And which is the control that you use that to establish the end of the drying process?
Well, it is, you can see it. So normally these dispersions, just because of the size, because they're about 200 nanometers in size, the particles, they are milky. So you can see that whenever they become transparent, you lose that milkiness from having the water still in the pockets. That's what we consider there. Right?
Okay, thank you. And I have a question. Could you please explain to us why is this effect of luminescent dependent viscosity? What is the reason for that? Why the luminescent depends on the viscosity roughly?
Yeah, it's just because if you look at the molecule, so you look at the molecule, you can see that these two configurations, there's a rotation from this configuration to that one.
Yeah.
So basically, when you are exciting it, it's in this configuration, and then when it comes back here, then that rotation is going to be more difficult if you're in a viscous environment.
Okay.
Not in a viscous environment. That doesn't make sense.
Very clever. Thank you very much.
The main thing is that these molecular rotors, as far as I know, they've been used for lots of biological applications. So they use them for measuring viscosity inside cells and measuring viscosity in lipid membranes, but it hasn't really been used much for these polymers, probably some more industrial applications. And that's where we want to go for. And also normally they only look at the general decay, they get just one value out of that. But like I said, what we are interested in is looking at the different components that are in there. It's quite challenging, probably.
Okay, other Maricruz.
So question for the presentation was very, very interesting and very nice. Thank you very much, Nacho. And the questions from the first part, did you see the roughness of the coatings with a different velocity of drying? Did you see big difference?
Yeah, you see differences, mainly because you can see like the colors, that the height changes a lot. So you have basically a film which is a blend maybe of latex and oxide of silica, and then at the top you have that superstructure which is only silica or only silica. So the roughness changes a lot because the height of those transparent and the FM going down and up. So yeah, the roughness increases significantly.
Okay, it's mainly related to the size of the particle that is on top.
Yeah, so if you see those structures, they are kind of somehow they look like hexagonal packing. So that's because if they are templated by the latex particles, we have the latex particles forming like hexagonal packing, then you have the superstructure on top. Those are the holes because the latex is happening. And the taller they are, the more rough.
And the other question is because I'm not familiar with this measurement of the lifetime of fluorescence. Can you measure in a very thick sample? And what is the depth that you are looking for?
Well, that's what I said. That's one of the things you need to check with the sample by sample. So the advantage of the lifetime is that if you are measuring like those cross sections that I saw the confocal, as you go in, the intensity is dropping down and dropping down and dropping down. The lifetime will be always the same, but there will be some point where it should not detect. But you don't have an effect of that. So that depends sample by sample. Up to now, we haven't had any problem yet with the samples that we have. And also those are dispersed, so they're not solid things. But it will depend sample by sample. So in principle, you can go, I don't know, what do you mean?
What is more or less the range? Okay, not exactly, but microns, it's.
It will depend on how good, if it is quite transparent, it could be much more microns. Like it is like really transparent. I mean, we've gone, I don't know, like a few microns in, we have some photovoltaic materials, which got perovskites that are like very absorbing from collaborators. We still are able to go through it, through the whole thing, but the crucible that's meant to absorb everything, and we can still go through. So I would say, especially if your sample is not very fragile, and you can increase this the laser, then I think you could go for it. But it depends.
Yeah, please.
Yeah, quite grateful. I had a question about one of your applications, the abrasion resistant coatings. That sounds very interesting. How resistant are they? I mean, how do you measure? Because we've also worked with abrasion resistance properties of adhesives, and I see you use latex here, which are very soft and which types of materials can you use these coatings?
So the coatings that we have, they are basically mainly for indoor applications, I would say. So that's one of the limitations, because we make materials that like water. So we use materials that like water. So if you are outdoors, they're probably not going to be that resistant. I think that they are more for walls, surface, that kind of those kinds of surfaces, pitches, tables. It will be more than a specialized application. It will be, because if you want something very resistant, you probably need to do something with solvents, things like that. You know, when people for coatings for boats and things like that, still using lots of solvent in water yet, because the solvent board materials they still overperform the water formats. But for indoor applications, I think that they are quite good.
Does the indoor, would they stand, for instance, like a kitchen knife or walking on the floor, or what sort of resistance?
No, I mean the resistance is more like wear and tear.
Okay.
You know, more an aggression. Like wear and tear of hands and maybe cleaning regimes or things like that. I think that we are looking at. But even not something like the people with an knife.
And being transparent materials in principle, is there any coloring effect of this? Especially the optical response, or when you use this coating, or does it change the color?
We haven't seen the change. These ones are not transparent. Those ones in particular, because this colloidal silica normally makes them white.
Okay.
So they are quite white, which we are trying to not make white. But for now, they are quite white.
Okay.
And we haven't noticed any color after abrasion, because you will probably still have silica inside. So you're not only, because really when I show you, well, I couldn't show you the video of the modeling, but in modeling, everything's really nice. It segregates all the small particles at the top, and the ones at the bottom. In reality, there's always some small particles that are also close to the bottom. So I would say, even if you scrape the top layer of silica, I think it will still probably look white. Because you will still have these lower layers.
Thanks a lot.
I see that there are no questions in the chat, so we thank the speaker once again. Let's see you again here soon.
Hopefully.
Thank you very much, and see you later.